Welcome to Hot Chips 22. Session 4, FPGAs.
Good morning. I'm Pradeep Dubey, your session chair for this session. And I work at Intel, in part of Intel Labs, Parallel Computing Lab. Brad Taylor is our first speaker. He's from Xilinx. And Brad is a PE there in EPP Architecture Group. And he has been working in this field for more than 20 years. And also, I should also note that you might think that he learned all his electronics during these 20 years, but he actually did prior to that when he did his studies in geophysics. Okay, so introducing Brad.
Thank you. Okay, it's a pleasure to be here and to tell you something about our new products at the 28 nanometer generation. Okay. So in this talk, we'll talk about the Series 7 architecture, which is our name for the 28 nanometer families. And of course, these give us some enhanced power efficiency, logic density, and I/O bandwidth. We'll also talk about a new architecture that we're rolling out next year called the Extensible processing platform, and our advanced interconnect system, which is which we're developing to connect all of our soft IP together. So before I go into the talk, I just wanted to talk a little bit about our motivation for this set of products, because one of the things that happens when we get to 28, and every time we scale, in addition to logic scaling, getting more logic, we also get more gates, and that really leads to more complexity. And in a certain sense, complexity really right now is driving our product line, because our customers are now being asked to develop logic systems, products that have several million logical gate equivalents on a very short time scale, and a lot of these products, especially kind of at the low end, are expected to be full system products. So that means they also have to include a programmable system, a software programmable system, in addition to the programmable logic. So one of the in that vein, towards that objective, the Series 7 logic family is based upon a new unified architecture which eliminates the differences between our different product families and simplifies the ability to for us to produce the product, for our tools to support the product, and also for our customers to adopt it. The Extensible processing platform is actually it's an SoC with a programmable logic accelerator or a programmable logic block next to it. But really, it's designed to be an SoC from the ground up. And what that means is that instead of designing an architecture, designing a programmable system with the processor and buses and memory systems, you're able to take this product and start writing code for it immediately while the hardware team is developing the IP that distinguishes the product. And then also, we're trying to address the complexity of simply integrating known grid IP. Our FPGAs are large enough now to incorporate multiple blocks of very complex IP, all of which has to work at fairly high speeds, and function, and it needs to be integrated together very rapidly. So we're adopting the AXI interconnect system from specified by ARM, the part of the AMBA interconnect spec, as a way of interconnecting our soft IP together. Okay. So we'll start with looking at the power, we'll start with looking at the process that we selected to for 28. So we're working with TSMC, and the first thing I guess to go over is this will be one of the first waves of, we'll be on the first wave of 28 products. In order to go to 28, we evaluated 3 different process variants. We looked at a low power process with a silicon gate. We looked at a high performance process with a metal gate. And we also looked at a high performance low power process which has a metal gate and and lower power or lower leakage transistors. So in our case, we optimized our basic goal was to reduce power while maintaining performance. And so we don't really take advantage of all the performance that's available in the high performance process. And what happens is, so I guess this is the process that we've selected. It's the 28 high performance low power process. It does have, it operates at 1 volt, and it does have a power advantage over both the low power and high performance variants. And the reason we get the power advantage, the static power advantage, is simply because the metal gate eliminates the gate leakage. We still have, if we set our process to kind of maintain performance parity with our previous 40 nanometer generation, we end up with about 2x the static power. Now, because this high performance process is lower voltage, actually the dynamic power will be lower there. But we feel that this is the best compromise for Xilinx products, and that's why we've gone with this. Okay. So the total result here is that we expect to see a rather dramatic reduction in static power, 65% reduction in static power compared to our previous generation, which was actually fairly high leakage. Dynamic power is a 25% reduction, and I/O power, we're saying a 30% reduction. Now, these are all kind of, whenever you talk about power, you have to know what the assumptions are. These are kind of our general targets, and they actually work out for a number of applications, but there's a lot of variation that you'll see depending on the design. We've also, most of the gains in I/O power didn't come from scaling, actually. They came from architecture, re-architecting the I/O plus a drop in our aux voltage, which is a kind of a bias voltage that we need. Okay, just to point out, Xilinx is also actively pursuing software-based logic power reduction through logic optimization, where we kind of, and this is actually a fairly significant reduction in power that we're able to achieve based upon basically disabling. What we do is we look into a circuit, and if a result is not going to be used on the next clock, we disable that flip-flop, and that actually contributes to about a 20% reduction based upon our benchmarks. And then we also offer our devices in a low power, low voltage option, -1 speed power grade, which gives another 20% power reduction. So we're doing everything we can to reduce power at this node. Just a little bit about the architecture evolution. At 90 nanometers, Xilinx had two families, a low power or a low cost family, and our mainstream high performance, high density family. At 65, we went to Vertex 5 and ended up with basically, this family began diverging from this one. So at 40, we unified them again around the 6-LUT architecture, but it wasn't a full unification. So now at 28, we are adopting the same architecture broadly across all the products, and we're introducing this new mid-range family. So the difference is that these are really distinguished by packaging, these different families. Artex is a wire bond packaging environment and limited to about 300K logic cells. Kintex is a bare die flip chip and really is a cost-reduced vertex device. The compromise that we made with Artex is we have reduced the performance somewhat in order to reduce the static power by a factor of 2, which is important in our low-end applications. So talk about capacity here, device density. If you notice, at 40 we were at 70-60K logic cells, and our newest Vertex parts are slated to go up to 2 million logic cells, which is more than you would get from scaling. This is due to some advanced packaging and assembly techniques that we're developing, which I can't go into much detail on. But the other thing to note is that we're also making an effort to substantially increase the amount of logic in our low-end, low-cost devices, up to 350,000 logic cells. Okay. This is a set of scatter plots that gives you a little more information about how the other parts of the FPGA vary. FPGAs are more, today they're far more than just logic cells. We have RAM, we have DSP blocks, IOs are always important, and we also have transceiver technologies become really a driving force for our products. So what this is, if you look at RAM and DSP, they basically track about the same. We have on the right side here, this plot shows logic cells across the bottom versus the amount of these special components such as VRAM and DSP. And so what you see is about here, we see the Vertex parts are off to the right, and then the Kintex and Artex devices. And really, the Kintex devices are distinguished because they simply have about twice the amount of VRAM and DSP compared to the Kintex devices, or the Artex lower range, lower cost parts. There's also a big distinction in the high-speed serial I/O. Kintex, or the low-end parts, have a couple of transceivers. With the mid-range, we have a few more, but we really get into high-performance serial I/O when we get into the new Vertex devices. And I believe this goes all the way up to 2.4 terabits of I/O bandwidth. There's a bit more on the I/O, serial I/O device improvements that we've been able to make. The difficulty here is that we don't get a lot from scaling, so we've basically gone through and re-architected our devices as well as we can in order to improve both the speed and lower the power. So at the low end, we get a modest gain. In the mid-range, we're actually going from 6 gig to 10.3. Then at the very high end, this is a new family that hasn't been announced, but we will be addressing a 28 gig transceiver in a future product. So the end result of this is that we're able to develop or demonstrate 300 gigs bridge with a total bandwidth of about 1.2 terabits in a part which we believe is actually competitive with an ASIC level implementation. And in this, we also show the total power that we save based by optimizing our transceivers. We were able to reduce the device power by 28% compared to had we not gone through the optimization process. Okay, our Kintex family, this is our mid-range family. And it's really the same as Vertex 7. It's just smaller devices in lower cost packaging. We'd like to use the lower cost packaging on the Vertex family, but the power requirements and the total number of I/O preclude us from being able to do that. So that's what Kintex is. The net result of, here's an example of a LTE radio mapped onto a Kintex device compared to our Vertex 6 devices. We get about half the power, same basic functionality at half the cost, and that's our marketing target, is to reduce the cost of these kinds of systems by a factor of 2 with this product. These products will be, our software is available now, I believe, or it's coming out shortly. And the first devices will be available next year in production in 2012. Okay, so now I want to shift on to this EPP, which stands for Extensible Processing Platform. I should have had that up there. I realized that we never actually explained what EPP is on this slide. So EPP is a SoC which includes an FPGA. And we believe this is actually fundamentally creates a new product class, primarily because if you think of an SoC, they're very good software programmability, have lots of great accelerator types or hardware IP blocks associated with them, but they're very unconfigurable. And the addition of the FPGA provides a large level of hardware configurability to the system. Additionally, the addition of an SoC to an FPGA gives us a really substantial amount of integration benefits compared to what you would normally do in an FPGA. This is a 28 nanometer based product. It's we believe that it has significant advantages over a discrete microprocessor and an FPGA, and those are just simply the benefits of integration. Cost, power, bandwidth, and latency all improve substantially when we bring these two devices together. This also, the SoC is based on ARM products, and so this also leverages the ARM ecosystem, which is very important to our customers to have a modern, world-class support system. We'll just quickly go over the EPP, and then because this is not an announced product family, I can't show you too much detail on the product line. So the EPP is a SoC. It's based on a dual-core ARM A9 with a set of memory interfaces and peripherals. This really does allow us to deliver ASIC-like cost and power in an FPGA environment. Additionally, because this is really based on SoC technology, it boots like a processor, acts like a processor, really is a processor from the start. It's conceived that way. And as a result, it's a much more straightforward device to use for an embedded developer. Okay. The extensible part of this is in this outer region here, which is we call the programmable logic area. This is really just our FPGA region. And in this area, we expect customers primarily to add common peripherals, common IP, and also to develop custom IP. So the use model for this really isn't fully defined. There is kind of an experimental aspect to this. When you take a high-performance SoC and you attach a large block of FPGA, there's a lot of things you can do in that FPGA that you can't do with two discrete devices. And a lot of that is just from the benefit of tight integration. So we know that our customers will be augmenting the processor with, say, additional peripherals or more peripherals that weren't included in the basic system. We also know that it's very common for our customers to develop these high high-performance, high-bandwidth processing pipelines based on FPGA logic, say for video processing. And it's also common to implement hardware like state machines in the FPGA to handle real-time events. So we expect those types of IP to migrate into the FPGA side. We also know there's some opportunity to offload the processor with FPGA, and Xilinx will be providing a number of DSP functions that can be used, such as FFTs, and for filters, standard DSP processing functions that can be used to offload the processor. The fabric in the ranges of the devices we're looking at is up to 0.2 tera max and up to 2.8 integer 16 operations, which is a substantial amount of processing all running at several hundred megahertz. Then there's a couple more experimental ways that we expect our customers to use the FPGA, and I'll just highlight these. One is to, sorry, I'm pointing at that screen. One is that there's a real opportunity here to offload power from the processor. I thought the talk yesterday was interesting about dark silicon. This is maybe another variant of that theme, because when you map an algorithm into an FPGA, you naturally see a substantial reduction in power. If that algorithm is accessing memory substantially, you won't see that because memory costs are very high power-wise. But in general, most operations, when implemented in FPGA, are about 10x lower in power than they are in a processor environment. So we'd like to see how this works out. We know that you don't always get the kind of optimal benefits that you think you might once you start pulling the data out of memory and out of caches and so on. Additionally, there are opportunities to use the FPGA to create heterogeneous multi-core systems. And we kind of see that we have an environment that allows an OpenCL-like environment to program these soft processors. Okay, this is a quick shot at what's inside the processor system. It's really a set of standard peripherals, dual-core A9 with L1 and L2 caches. It's pretty much what you would expect. That's at least what we're shooting for. Because this system is independent of the FPGA, it's able to program the FPGA, and it's able to do it using, say, non-traditional programming methodologies, such as downloading the image from a network, from SDIO cards or USB cards. Key to this technology really is this interface to the FPGA, and there we're using the AXI interfaces, multiple AXI interfaces. And these are really targeted at providing the full bandwidth of the DRAM system to the FPGA side. And our goal is to not let the interfaces be the limit or not to limit the system performance because of limited interfaces. The software, the development flow for this, we really see as being kind of a standard flow where there's a software side and a hardware side, and teams work independently using their own tools, and really the convergence occurs through system architecture. This is a little different from our previous generations. I'll just talk about that quickly. Previously, we've had a soft processor, the microblaze. We have the PowerPC, which is a hard embedded processor, but without the SoC side embedded in the FPGA. So it required soft logic to implement all the peripherals and the memory system and the bus system. And that really made the design fairly hardware-centric. And what that really meant is you had to hire a hardware engineer to build the system, architect the system, and then maybe 6 months later you could start writing software for it. This drove a number of customer requests to build, to make the system more programmable out of the box. Using standard CPU architectures so that, based on open standards and ecosystems. And hopefully we've addressed these with the EPP. We still believe the microblaze is very important. Many IP blocks are complex enough they need their own internal controller. And that's where microblaze is targeted. Especially with a high-quality processor running Linux next to it, the microblaze can offload a lot of the system-level functions that it didn't do as well to the main system processor. Okay, we'll talk briefly about our new interconnect system. It's based on AXI. It's an open standard from ARM. It's a very high-performance interface, very easy to use, lots of features, and it's kind of the interconnect of, we never had the option of using something like this in an FPGA until our devices got large enough to really require it, and also so we could afford the complexity of adding a real switched interconnect fabric. AXI AXI itself is an earlier standard, but AXI 4 has just been released, and it has some variants which are good for FPGA, something called AXI Lite, which is a very low-cost implementation, and AXI Streaming, which is even lower cost. I don't think I'm going to have time to go through these details, but the AXI 4 base protocol has 5 channels, all of which are independent. Both the read and write channels are independent from each other. The streaming AXI variant is really just a data channel with a ready valid handshake, and it's a way that we can connect our streaming IP together. This is the primary block that Xilinx is making available to our customers. I should say that we've also ported all of our IP to this AXI, or not all of it, but 50 IP blocks to AXI interfaces. And this is what allows you to connect them all together. Instead of a bus, you use this AXI interconnect block, which connects masters to slaves. And the register slice, each port offers protocol conversion for clocking, for data width, and configurable 5-point buffering, basically. Okay, I think that's about it. I guess I'm ready to take questions.
Please identify yourself and go ahead.
Good morning. John Swan, Swan on Chips. I'm also chair of the local computer society, so you'll see me out by the computer. Who am I asking a question to? There's 4 names on the presentation here.
Brad. Oh, I'm Brad.
Brad. Okay, hi, Brad. This idea now that you have the processor on with the FPGA fabric is really going to make it, really a big tool in a toolbox. Being able to take the software and push it off onto hardware, right? There's been tools that have been introduced to do that. Some have been pulled off on the market. So what's your plans for tools and that? Is that going to be an internal tool? You're going to be working primarily with external vendors? And then secondly, from a system designer standpoint, I would want profiling tools that allow me to know where to partition both functionally and as far as data flow. So that's another set of tools that would support that cool methodology.
So our current plan is primarily to leverage the ARM ecosystem for tools, for software tools. We've decided that it's still a little too early to try to automatically detect hotspots in the code and move them into hardware. So we still see that as a kind of a manual process for some period of time. What we hope is that this architecture makes this viable enough that those automated tools can be developed over the next couple of years. Does that answer your question? Okay.
John Davis, Microsoft Research. I got a couple questions. The first one is, can you talk about the memory interface for the DDR controller to the ARM cores? Are you doing some type of controller that's expecting an off-chip memory, like a DIMM, or is it going to be something internal, like a 3D stacking? Well, I guess it's kind of ambiguous intentionally there, but it is an off-chip. Chip memory system. So there's a lot of opportunity in this kind of environment to closely integrate the memory in, but we haven't taken that step yet. And then in terms of the tools, right now it takes a long time to compile, do synthesis, PAR, all that stuff. For currently available tools and generations of Xilinx parts. Going to 2,000 cells, what are you doing with the tools?
Yeah, 2 million logic cells. It's a real, well, what we hope to do is we keep buying better Intel computers that run micros, that run faster. It's always a challenge. I've noticed that the benchmarks I'm running now are taking about the same amount of time that they were 5 or 10 years ago, because even as we keep introducing new FPGAs, we are just barely able to keep up with the software task. And it's still true that a compile for an FPGA, even a fairly small one, can take hours if you push things.
And this would be days?
What's that?
For the largest chip, would this be days? For the compile time?
Days?
Yeah.
Well, to be honest, you're probably going to want to do some type of hierarchical partitioning there, so you can break it up. But we don't think it should be days.
Thank you.
Ilya Ganusov, Acronic Semiconductor. The talk by Schlumberger yesterday, they mentioned that one of the things they wanted from FPGAs was new domain-specific languages. Do you have any comment on that? Are you working on this?
Well, unfortunately, I missed that talk, but I do think that if you're designing hardware flow graphs, domain-specific languages make a lot of sense. Xilinx does offer a tool called System Generator, which operates inside MATLAB, which is really designed to build data processing pipelines efficiently, primarily because it's a simulation environment that also, as a kind of a byproduct, generates hardware. Yeah, we'd be open to any innovation in that area.
Thanks.
Let's thank our speaker.
Okay, thank you.
So now that you heard from Xilinx, now the next talk is from Altera. And Dan is our first speaker, and actually Sergey would join him soon after during the talk. So Dan Mansur is director of Altera's communication business unit. Over the last 9 years, he has been responsible for FPGA product planning and Altera's technology office. Sergey, Sergey Sumarev, I hope I didn't butcher his name, is director of Altera's analog design team, and over the last 14 years, he has been leading the analog development and over 5 FPGA generations and over 100 SerDes patents. So let's welcome Dan.
Good morning. Today I'll be introducing our Stratix V 28 nanometer, 28 gig transceiver integrated on that 28 nanometer product. We're actually going to be coming out with multiple families in 28 nanometer. There'll be a Cyclone, Aria, and Stratix. Today we're just talking about the Stratix. That's the high-end platform. There's a mid-range, and there's a low-power, low-cost version. So this particular family is on our Premier family. Will be coming out first. The good news is the software is completely available today in the public domain. You can start and compile your design today for 28 nanometer. There's a 1,000-page data sheet online. All the details of what I'm talking about today are online, and you can get silicon first quarter of next year. Now, within that, we've actually developed 8 test chips. Today, we'll be showing multiple transceivers driving across customer backplanes on real silicon today. So the test chips actually incorporate multiple lanes. They incorporate the PMA, the PCS, logic, noise generation, be able to isolate the transceivers. This just shows the target markets for the high-end FPGAs. And certainly communications and broadcast are the 2 premier ones that are on high growth today. What I'm going to talk about is the process. And we just talked about the process at TSMC, high metal gate. And one of the points made was static. We're all going to worry about that. Static power is one of the key parts that you have to worry about. If you go to a performance process, you have to mitigate that static power. Now, what we do to do that, and this is our 3rd generation of doing it, is we actually do adaptive body biasing. You can forward or reverse bias any part of the FPGA down to 1/10,000th, one lab, one logic primitive. You're able to either forward bias or back bias. And that pays huge dividends on your design, because it's your design, is actually compiled. The synthesis tools go in, find out where your critical path is. On that critical path, which is about 20% of the design, we can forward or back bias for performance. So you can go high performance or low power on a per design basis for each one of your compiles. Now, in addition to that, we can also use those facilities for manufacturing. It enables us, for all the variation we talked about the last couple days, it actually helps us mitigate that variation and enables us to produce the devices better. So there's two key components that we can produce, these large FPGAs that are over 500 millimeters squared in mass production. And we're doing that today in 40 nanometer. We're taking those same facilities, which is the body biasing and also redundancy. The entire FPGA is fully redundant. If there's a defect density anywhere in the FPGA, we can repair that, and we can actually manufacture that past the defect density curves. So we can manage defect density. We can manage chip variation. We have full knowledge of what's on the chip. We have the process knowledge. We have of that specific device. We have the voltage knowledge. We have different test structures within the device. We can accommodate that by actually using those methodologies for manufacturing. Whoops. Stratix V. These are the high-level features, self-explanatory. The two key points I'm going to be highlighting today are the transceivers, which gives us really the bandwidth. This is the bandwidth family. Exactly was mapped out earlier. You can see different families have different needs. Some of them have fewer transceivers, fewer memory on it. Some of them have higher transceiver counts and a lot more memory on it. This family is the bandwidth family. It has a lot of transceivers, it has a lot of memory. In addition to that, to really make it useful, to take advantage of the FPGA, which is the most valuable resource of this chip, is we have to lower the complexity and cost of getting in. So we actually put on hard copy blocks inside the FPGA to be able to lower the cost for things like PCI Express and various protocols that are fairly sophisticated and difficult to design. So we want to take care of that for you. And basically, we employ a hard copy methodology for that. Hard copy we've been working on for many years is a metal programmable entity that actually reduces the size and cost and power by a factor of 20x. So it's basically it's a hard ASIC methodology that's via programmable in metal. Keep going back. This is a typical FPGA family. Across the top, you can see there's three categories here. It's, here we go. The interconnect, the hard IP, and the core fabric. And you can see all the attributes within those here. And here you can see different device families within the family where actually, once again, we adjust for high memory and DSP blocks or for higher transceiver count or faster transceivers. There's variations. And this isn't the whole family. There's multiple devices coming. They'll be announced shortly that fill out the entire Stratix family. But you can see we have some that are focused on certain transceiver strengths, high-speed transceivers. These are more memory and DSP, and there'll be a bunch more devices in this area. What I wanted to highlight on the next slide here, I'll be talking about breaking down each of these components and what we do for innovation with these. These are basically just to get into the device, and I'll be breaking down exactly what we've added to here, and we'll talk about the detail of the transceivers. The hard IP is actually what we'll show. We'll do multiple variations of that hard IP. OK, so those three blocks that are very FPGA specific. The logic. You tell us what to do. In your EDA tools, there's something called talkback. We watch exactly what you're doing. We watch how the data paths are getting wider. We're watching how the Fmax is going up. You have to pipeline more. And we're adjusting the logic each time, optimizing it just a little bit and a little bit for exactly what you're looking for. So we actually put in more registers, more ability to be able to adapt. We've gone to a wider LUT structure as well as additional registers within that LUT structure and to be able to be more flexible within that LUT structure. It's just that we're putting a lot more memory on. We can tell exactly how you stack that memory with depth, width, bandwidth within those memory constructs. In addition to that, we watch exactly what clock networks you have. We put in a huge amount of new facilities for that clock network so you can lower your cost for external components. And we should be able to give you pretty much any clock. The clocking structure within FPGAs is phenomenal today. It really is amazing. OK, power. This is a little more the detail of power. We attack it in two different directions, static and dynamic. And we can self-explanatory what we attack. We'll break down exactly what this power is for the 28 nanometers in a few minutes. And we'll show that it's world-class. It's less than 8 milliwatts per gigahertz of speed on the transceiver. In addition to that, I'm going to highlight kind of something a little bit unique is that one of the nice things about hardening in this IP is it lowers your cost and it lowers your powers too, both on a static and dynamic, as well as we can turn them completely off and you never see them. Completely zero from power standpoint. OK. This is just a simple representation of it. There's logic. There's the DSP blocks, the memory blocks I mentioned. these fractional PLLs, which brings in a whole new ability to get the appropriate clocking coming in. You can have up to 44 different kinds of frequencies all coming in off those transceivers. And we can accommodate those into the fabric. And then there's this little brown thing right here, this column right here is called EHB, Embedded Hard Copy. There's as much functionality in this little strip as there is in the entire device, because once again, it's about a 20x reduction of density within that. And what we can do is we can put in PCI Express, we can put in QPI, we can put in Ethernet, we can put in all kinds of facilities, once again, to make your life easier of getting into the FPGA. You should be able to plug your card in and bring it up into any Intel complex with PCI Express 3.0, auto-negotiated, and it can actually bring in POPs through that PCI Express, POPs being the programming object file. So it should be much easier, as well as lowering your costs and giving you more density on the FPGA to do the things that you want to do. Now I'm going to break down exactly what this looks like right in here, and then we're going to talk in detail about the transceivers. Within the transceivers, we have the hard protocols in this block. We also have some full standard cell components that absolutely need speed for the deserialization, encoding schemes, and then we have the PMA section, and then this clock network. That clock network is very sophisticated and gives you the Swiss Army knife of transceivers. So there's well over 100 PLLs in this chip. It's a lot of PLLs. And I break those down right here and show you some of them. We have some supporting the 28 gig transceivers with an LC structure for that PLL, which we'll be talking about in detail. We also have ring oscillator-based PLLs that give you a certain range. Each of those PLLs is there for a function that's unique, but it ultimately works all together, so it gives you a transceiver that can take any speed from 0.6 to 28 gig. Each of those PLLs kick in for their optimized region. Those optimized regions have to meet the jitter standards that are required for those specifications, which we'll show you a little bit later. So over 100 different, well over 100 PLLs supporting up to 44 independent channels of traffic coming in. This is just an example of the hard IP. PCI Express, Ethernet, interlocking, the typical things that you should expect us to help you and validate and give you runtime configuration to those and lower your complexity and cost of the FPGA. The memory controller, highly configurable, gives you plenty of speed, and it's ubiquitously placed on all the user I/O. So with that, let me move on to the transceiver with Sergey.
Okay, good morning, everybody. Let me share with you some of the transceiver details as well as the 28 nanometer the results from our chip that we built with TSMC. So first, there's just a high-level overview of the transceivers. We have two types of transceivers. We have the 28 gig transceiver that has a continuous native range from 20 to 28 gig, and its goal is to be CI 28 gig compliant. We also have a separate transceiver types as a 12 gig transceiver that is supporting from 155 megabits to 12.5 gig. And its goal is to be SFP plus compliant as well as to meet the KR compliance goals. The transceivers are independent, so you could configure each channel independently from the other channels without interrupting the traffic in FPGA and on those other channels. On the technology side, we have both LC-based PLLs and we have the analog CDR and LC-based PLL allow us to produce best-in-class jitter, while the analog CDR is there to get the best jitter tolerance we can achieve. On the signal conditioning, we have all the techniques, and I have a separate slide listing them, but there's basically all the techniques available there to meet your signal conditioning needs. This is a sort of a quick overview of all the features on a transceiver. These are, in general, the features that you would expect from any transceiver offering, and I'm not going to dwell on them except for this on-die instrumentation. This is the new feature that we have introduced on the 14 nanometer, and we have expanded it significantly on 28 nanometer. And I would like to spend a couple of slides sharing with you some of the details of on-die instrumentation. The goal of on-die instrumentation is to monitor eye margin in the receiver as you receive the eye from the link. And as a result, you can evaluate effectiveness of the various signal conditioning techniques that are available in our devices or in the other devices as they drive the link into our device. So with that, let's take a look at the regular sort of conventional link. So you have a transmitter with the preemphasis that will precondition the signal and launch it into your link. Then after the link, you will have attenuated signal, and that will be also dispersed. And then you would receive this signal into your receiver, and you might have a different type of equalizers there. For example, in our case, we have both continuous time linear and decision feedback equalizers. And finally, you have a clock data recovery that the whole sort of purpose in life of clock data recovery is to now recover that I. So right before the clock data recovery here, what we have is IQ iViewer. And what it does, without interrupting the mission mode traffic, it is able to scan the eye horizontally and vertically and give you the eye contour so that if you exercise different preemphasis, different equalizer, you can see what difference does it make within the transceiver itself right before the CDR. So the way it does it is, this is the block diagram of it. So you have conventional receive path that has equalizer, and you have a CDR here with the phase detector and so forth, and the mission mode sampler, which we call sampler A, that now samples the receive eye and gets it to the deserializer and then sends it into the parallel world. On top of that, you have a replica sampler that is now being controlled by the clock through the phase interpolator, where you can, independently from the mission mode sampler, you could change the position, both horizontal and vertical position of that clock, and as a result, you can sample it into the separate sampler, and then so that what we also added here is the at rate bit by bit checker. So you could compare the difference between these two samples, and then it's being parallelized, and the information is being sent into FPGA. So we have 64 vertical steps and 32 horizontal steps, and this is the results from the 28 nanometers that we have tested, and you can see we can just step through and get the eye here. Now, switching the topic into the power, going from 14 nanometer to 28 nanometer on our mainstream 12 gig transceiver, we have achieved 50% power reduction. And this is now at 11.3 gig because our 14 nanometer family went up to 11.3 gig. So this is the reference point. So what I have plotted here for you is the power of these two transceiver classes that I have described earlier. One is the 12 gig transceiver, and you can see its power over different data rates. And the last bar is the 28 gig transceiver power. So the left-hand side shows the total power in milliwatts, while the right-hand side, reference to this curve line, shows power per gigabit. So you could see some interesting trends, is that whilst the mainstream transceiver going from 40 to 28 nanometer, we have reduced the power by 50%. The introduction of the 28 gigabit transceiver changes the power game significantly, as the power per gigabit is just drastically dropping here. So let me show you how we spend our power. You have, this is 28 gig transceiver, and you have two types of power numbers. One is the sort of base features, and the other one, some of the additional signal conditioning enabled here. So the first 25 milliwatts we spend in our linear equalizer, and then in a CDR we spent nearly half of our power, and that was 98 milliwatts. Then in deserializer we spend another 28 milliwatts. TX driver spends 30 milliwatts, and in a serializer 20 milliwatts. So that comes to the total of 200 milliwatts per 28 gig channel, and if you divide it per gigabits, you get 7.18 milliwatt per gigabit. If you want some advanced signal conditioning here, like a DFE, you would need to spend another 35 milliwatt, and you want to put some more preemphasis, you spend 11 milliwatts, so that would come to 8.82 milliwatt per gigabit. We believe this is the best-in-class power that is available right now on this technology. Some of the measured results. This was collected in July, so it's somewhat old, but still, nevertheless, it shows the 28 gig signal on 28 nanometer, just working fine. So being the circuit guy, I really like to look into the actual the chip picture, and this is the 28 nanometer chip picture. So you see here 28 gig channel. You see here 12 gig channel, and there is more channels there, but I just wanted to zoom in into the both 28 and 12 gig. You also see here LC PLLs that are sort of stacking up, and you see one of them here. And what's interesting here is that sort of comparing the 12 gig and a 28 gig channel, you can see lots of RF techniques here, lots of inductors have been placed in the 28 gig channel. Also, obviously, LC has its own set of inductors, which allows that produce to continuous range of operation. What is not visible here, and I would like to sort of share with you on the next slide, is that there is even more sort of RF technology that allows the 28 gig operation. So, for example, under the RX and TX bumps, under each bump, we have placed these inductors, and they're not visible, obviously, on the prior picture because they're sort of under the bump. But what it allows to do is to tune out the capacitance of the bump so that we can meet the return loss at 28 gig, and we can produce the I diagrams, and we can receive the signal. So there's a lot of die package RF co-design that is required at these data rates to enable this technology. Some more results on 12 gig channel. So the 12 gig channel is intended to address both 6 gig and a 12 gig backplane. And whilst it's important to address the 12 gig backplane, the 6 gig backplane market is also quite large, so we cannot compromise the performance of equalizer at 6 gig backplane. So we had to change equalizer from the 40 nanometer so that we can simultaneously produce the picking either at 6 gig, or we could shift the picking to the 12 gigabit. And the same equalizer could basically work in both cases. So since this was a change in the equalizer design, it was one of the first things we have tested in May of this year. And you could see that 12 gig signal, obviously without equalizer, is fully closed. And once we shift the picking into the right position, then we can completely open it. This is the 12 gig signal going over the legacy backplane on 28 nanometer. Lastly, let me show you the boards that we have built, and we are sort of demoing them all over the world right now. And it has both the 40 nanometer companion FPGA as well as the 28 nanometer chip that I have shared with you the results of just now. We have the backplane connectors, so we can connect into the backplane, and we can show the performance of 28 nanometer test chip over the backplanes. For those people that would like to actually see the signal, we have added both the SMA connectors for the 12 gig and MMPX connectors for the 28 gig. You could see there is the pair for the RX and a pair for TX, and so one channel is broken out in both cases. And there's other auxiliary elements on these boards that I'm not going to really cover. With that, any questions?
Ilya Ganosov at Xilinx Semiconductor. Very interesting talk, very exciting development. These are all the results from the test chip, right?
Yeah.
I haven't seen any roadmap for rollout of the products. When are they going to be available on the market? Okay.
Samples, broad base.
And the next question I have, it seems like because of the great increase in the total available bandwidth, the total number of lots on the core is actually lagging behind in terms of a percentage increase. Do you think there are going to be a big class of applications which, because of the limited speed of the core, will not be able to take advantage of this bandwidth?
Well, I track logic bound, memory bound. I can tell you most of their designs are not logic bound or memory bound. They're usually memory bound or transceiver bound. So we're seeing more bandwidth applications. There is an inherent, performance of the Fmax, the FPGA is saturating. And with that, there are going to wider data paths, and hence you could argue that that would increase the amount of density that's needed. And I do think that the FPGAs are doubling their density to accommodate that. So we are doubling density, not performance. But I don't see a significant amount of designs that are logic bound.
Okay, thanks.
More questions? If not, let's thank our speakers and we can catch up on.
Thank you.
And now moving on from 2D FPGAs to something different, 3D FPGAs. FPGA of FPGAs. So our next presentation is by Raminda Madurawe, and he's founder of Tier Logic. He invented 3D FPGA, more than 25 years in PLD FPGA industry, and impressive, more than 106 issued patents. So let's welcome Raminda.
Hello, everyone. Can you hear me? Today, I'm going to shift directions a little bit and talk to you about what's under the hood, the nuts and bolts of an FPGA, what I personally believe that FPGA technology needs, whether I do it or somebody else does it, how we can move this into a much more appealing, useful aspect for the users. My name is Raminda. We have a concept on 3D FPGAs, and the basic idea is how can you increase the density, performance, power, improve of these with a different approach into how you build the engine of a programmable device. So with that, the first thing is if you open the hood of a 2D FPGA, what do you really see? I claim this the forest. You can grow whatever trees you want, but it depends on how much rain you get in the forest. So you're limited, but what's available for you. So in a 2D FPGA, it's inherent in a programmable architecture that there is a significant overhead related to two specific components. One component is the muxers. Those are the switches that you need to get your programming into the point you want. And the second one is the configuration RAM, which holds the instruction to program the mux. As a result, these are all intermixed. The distances between 2 points of logic increases, the wire loading increases, the capacitance increases, the resistance increases, so you have poor performance, poor power, and extremely high cost. Some people will argue that an FPGA is 30 to 40 times poor in density over an ASIC, 3 to 4 times poor in performance over an ASIC, 10 to 15 times poor in power over an ASIC. A lot of people have tried to do a second design, but the simple fact of the matter is it's a complete redesign. Nobody really wants to spend their time and effort on redoing something you've already done before, so it ends up not getting done. If you look at the programmable technologies, SRAMs won in the long run because they scale with process technologies All other technologies such as EEPROMs and E-squared and fusers kind of died along the way because they just didn't scale the voltages, etc. But if you compare a configuration RAM cell for stability and for lower power over a memory cell and track it over the last few generations of process technologies, people are paying, or the two-dimensional FPGA guys are paying a significant overhead for this configuration RAM compared to a memory cell. Plus, as you get to 28 and 20 and 15 nanometer technology, these memory cells are not as stable. There are single bit errors. You have to have multiple power rails and a lot of other constraints that add as an overhead for this technology to scale. Therefore, a simple thought process is, why can't we remove some of this programmable overhead and put it into a second story? If you want to build a house in Palo Alto, because the real estate is so expensive, you're better off putting some of the stuff into a two-story house rather than building a single-story house. Now, if you can stuff all the extraneous circuits into the second story, then you're left with what you need in the first story. So the logic is closer to each other, the distances are shorter, the capacitances are less, the resistance is lower. So you get a power benefit, you get a performance benefit, and you get a cost benefit. After all, building materials are cheaper than real estate. So we can make use of that advantage. A second thing is, once you construct such an FPGA, the configuration memory, in this particular case, the middle picture, that is sitting on the second layer, it only holds zeros and ones. And 0 and 1 is very easy to duplicate in a ROM. It's a simple metal layer. Whether you connect it to power or ground becomes a very simple matter, as long as you know what that bit pattern is. So as a result, without changing the first story of the house, you can easily replace the second story, which happened to be your configuration layer, by a metal layer, and you have firmed your FPGA design into a relative ASIC type design, which is more reliable. It does not require boot ROM. It does not have single bit errors. It has a lot of advantages compared to all the disadvantages you face with an FPGA. The second most important thing is, if you are a designer, once you do the design, you can move on, because your ops guy can decide when the volumes pick up that he wants to firm it and go to a cheaper platform. Because after all, when you go to the cheaper ASIC platform, from a process point of view, you don't have to build that second story because you metallize it. That's point one. And point two is, there are so many muxers in this particular structure, and all the muxers are in the ground floor because it's in the timing critical parts of your design. When you have a 20-to-1 mux in the FPGA, all 20 parts have to work. When you hardwire it, you only use one of those muxers. It's almost like a redundancy kicking in, because the other 19 muxers are don't cares in this case. So the inherent yield improvement that you get with hardwiring gives you a significant cost advantage when you migrate from an FPGA, which is a 3D, to a 3D ASIC. So to put it in a pictorial representation, in an FPGA, you have static control of your circuits, whether it's a pass gate or whether it's some kind of an inverter. They're all static nodes. So as a result, you don't need a lot of drive current to drive these static nodes. Some people call it, you need a snail. And the snail operates a pass gate where the race horses go. And in 2D FPGAs, you have a very high-powered, high-performance SRAM bit controlling that gate, and that's not necessary. You need a poor man's SRAM cell, and we have decided to use thin-film transistors for that purpose. They're not high in mobility. They are very poor in mobility. They can drive nanoamps on currents, enough to charge a static node and keep it at the voltages you need. But once you've designed it into that tier ASIC methodology, then when you replace it with a power or a ground bus instead of ones and zeros, then you have frozen that design from your SRAM array into a ROM array. But the nice thing is you can extend this concept further and say, gee, that control node, I can mux it, also using a poor man's mux transistor because they don't need to be high performance. And you can decode such an arrangement, and you can connect it to multiple ROMs so that you can switch your entire ROM programming array from any one program to another program with relatively little time and reconfigure your device on the fly from one application to another application. A big problem in FPGA reconfiguration is you cannot go into your logic and decide which wires run into contention. So there is a big power problem every time you try to configure an FPGA, because the contention for a certain amount of time, you go through that while you are fully configured, and people have to worry about how you configure it. So this on-the-fly configuration of all FPGAs are very power hungry and extremely difficult to do, and something I would like to stay away from. But on this technique, because you can configure the entire configuration layer very quickly in one cycle, you can avoid a lot of those problems. So the nice thing is you have an FPGA when you want it, you have an ASIC when you want it, and if you are interested, you can even have a multiple ASIC in the same footprint if you want it. So when we built this, we decided to use monolithic construction techniques. So we used thin film transistors. I looked around in the industry, and I found that only the display industry used thin film transistors. Unfortunately, they were using 10, 12, 15 volts, and we needed a couple of volts transistor. Luckily, these are all silicon transistors, so you can use E-field scaling. So on the back of an envelope, we calculated what should it be, and we went and plugged it and ran a process and got it. And on the first silicon, they behave exactly what a simple calculation tells you how these transistors look like. So what we did was we took a standard CMOS process, and at the very top, above the top layer of metal, we bolted the thin film transistors, and so from the very top, all you see is a memory array. It's very nice array. Each of the bits goes straight down and gets connected to one of the transistors at the ground layer, and it programs that particular node. We needed a large number of bits, roughly 1 bit per 2 to 3 square microns to get this done. So at that density, it's not possible to do die-to-die attachments or different kind of arrangements, because in the through connections, we still have to have a lot of metal wires that go through. If you know, programmable logic is selling people wires and very little logic to go with it. So everyone is happy with the programmable aspect of it. We had to maintain temperatures less than 400 because it's already metallized, and the copper interconnect underneath doesn't like to see temperatures over 400 because of migration and disturb issues for the metal layers. But we were able to do that, and the second picture shows at the very top, now we no longer have the thin film transistor layer. Instead, what we have is that top layer metal either connected to a power bus or connected to a ground bus. And by doing that, we mimic a 0 or 1 pattern in the ROM layer, and we hardwire the underneath silicon layer to one specific instruction set that you would program an FPGA. So the nice thing here from an ASIC point of view is it still holds and maintains the bitstream concept of circuit design. What the bitstream concept does is all the metal wires are prearranged. From a tool's point of view, the delays and the timing arcs are all pre-characterized, so it's very easy for it to go take those numbers and give you a time enclosure just like you would in an FPGA. So the nice thing is any FPGA design, we can port it to either of these two devices within a matter of hours for us. Thin film transistors. We decided to build N and P type TFTs. Typically in the display industry, you only find N-type TFTs. And that's because the P-type TFT mobility is a lot less in amorphous silicon as compared to N-type TFTs. We also invented majority carrier devices. So as a result, these are like resistors. You apply a voltage on the gate to deplete the channel so they become off. So when it's on, the channel becomes a resistor. And they work on an accumulation mode. And using this, we were able to put together a 9-transistor TFT cell, 9 transistors so that we could decouple the SRAM bit from the underlying logic switching silicon, so the noise will not disturb any of the latches. And we found that these bits consume extremely little power, under 10 microwatts. It's actually less than a microwatt per million bits. So compared to typical SRAM cells, these are pretty much non-power consuming devices. They are extremely stable on ion to I-off ratio. And the nice thing with an SRAM cell is it's not a dynamic circuit. It's a static circuit. So only during power on and during configuration, you need to switch these devices. For the rest of their time, they are static. So there is no power generation, there is no cooling effect, so the integration is very easy, and you don't have any difficulties that people try to do in a 3D IC, because power becomes a difficult issue for a lot of these people if there was a lot of switching in a second dimension. This is to show some transfer curves of the latch to show that just because they are thin film transistors doesn't mean they work any different from CMOS. I was mentioning to one of my good friends who was founder of my previous company, and he turned to me, he's a Stanford guy, and he said, you know, Raminda, before high mobility transistors came to be, people actually use amorphous silicon and polysilicon transistors in the industry. So if you go back 40, 50 years ago, that's what people did. So it's just that we forget that's where this industry came from. So we don't have any issues. VTs are considered a little bit unstable for thin film transistors. But the nice thing with a latch is you really don't care what the VT is, as long as the devices trip. And they are very low power. They are static circuits, so it's an excellent 3D layer for people to scale their geometries. You don't have to go to 28 or 20 nanometer to get an advantage in process scaling. You can go up in space and try to get a little bit of that. So how do they scale with E-field? This is a graph across 2 orders of magnitude in lateral E-field, and in the vertical scale, the current. And what I have done is I have normalized the off current and on current to fall on a linear line. What that means is you can take any operating point you want, and you can back calculate whatever the parameters you want to build these devices, and they will work exactly as you would expect them to work. These actually scale better than CMOS, and part of the reason is that the geometries I use are not pushed to the same as the 28 or the 40 nanometer regime. For a 90 nanometer CMOS front end, I'm only using 180 nanometer channel length for the TFT transistor. So when the front end will go from a 90 nanometer to 40 nanometer, I only need to go to a 90 nanometer channel length. And we've already built transistors that were smaller than 90 nanometers in thin film transistors, and shown that if you just scale the voltages, they just work fine. That's not a problem. So where does this go? The first step, I believe, is in this migration, in the vertical migration, you get rid of your static circuits, which is your SRAM circuits. When I look at the die, after we did this, so if we go and take a look at it, about 50 to 60% of the remaining area is consumed by muxes. So the obvious thing is to say, gee, can you actually port these muxes into another vertical layer? Because after all, the mux is an on transistor or an off transistor. So if you conceptually look at it, at the end of the day, it's a piece of metal or it's a missing piece of metal somewhere. So you can always get rid of a complicated mux structure with a simple metal structure at some point of time. So if you do that, there's an easy another 2x improvement to have had in this particular structure. And when you do that, you can put this into a significantly higher density area. To give you an example, at 90 nanometer, the number of LUTs we get per millimeter square is similar to what a lot of guys get at a 40 nanometer density point. So if we increase it a factor of 2 beyond that, that's pretty much close to what a lot of people will get at a 28 nanometer density node. But we are still at a 90 nanometer density node. So this kind of thinking, I think, leads to a very high potential of getting logic density without really have to go to a lot of complicated processing solutions that people have to do today at the leading edge technologies, not to mention the mass costs of those technologies. So if you were to draw a cube, I was trying to be an artist here, so please excuse my attempts. You have a 2D FPGA where the NRE is very low, the gate density is very poor, and the unit cost is extremely high. And in the opposite end of the cube, you have an ASIC where the gate density is great, and the unit cost is great, but however, extremely high on the NRE. So what we are attempting to do is to take a slice at a time into the direction of an ASIC. The first slice is this three-dimensional FPGA concept, where you move the configuration memory into the second layer, and that gives you an FPGA and a matching ASIC. The next slice of the onion, so to speak, is to move the muxes in the vertical direction. Then that will give you another step into the density arena. And they both give you this nice concept of you design to an FPGA and you can freeze the design in a much cheaper, simple, pure ASIC form, which is uses a CMOS technology. So it's a duality of designs with a single design. And of course, they also lend very well to all these embedded type of concepts where you can have programmable cores mixed with any other type of cores, so that can give you a high flexibility in what you want to do. So just to summarize, this is, I believe, a very simple and easy way to get a much richer programmable logic fabric without having to go to some of the more expensive and costly process nodes in the industry. As a comparison, I put together what I believe is how people calculate LUT densities in per millimeter squared at different process technologies to show that in a typical two-dimensional technology, you get roughly a doubling of LUT densities per millimeter squared, and it's not quite double. It's not following up to Moore's law. It's a little bit less than that. Over 6 nodes of process scaling, people have achieved about a 40 times improvement in the number of LUTs you can get per millimeter squared. So on top of that, if you add the 3-dimensional technology, the first 2 data points show if you were to just take the configuration memory into the second dimension, how does that density work in terms compared to a 2-dimensional technology. The third point shows if you were to take the muxes as well as the configuration memory, how does the density grow? And it clearly shows you that going into a future, for a lot of users, this gives the capability of providing very high LUT densities per millimeter square. So I have a busy slide here. I wanted to give what I call the 20,000-foot view of why do we get all these advantages? What's the mechanics behind it? This is only a first order analysis. You can always fine tune it with a little bit more complex analysis. And the first column is taking a look at the 2D FPGAs. I have been very generous to the amount of logic per millimeter squared. I have seen publications that claim the percentage logic is 3 to 4%. It depends whether an ASIC guy writes it or an FPGA guy writes it. So you have to kind of massage the data. I have been generous because I put in a few repeaters and a few buffers into logic, because even in an ASIC you do have to provide some of those features. So it's roughly about 10, 12%. The configuration memory occupies about the quarter of the slide. And the routing, which includes the muxes and the buffers, can be 60%. I've seen numbers as high as 75–80% for the routing part of this. Right? So the second column, so here, one fundamental and important point to remember is the number of wires that crosses over your logic unit. That's the number of wires you use to route whatever the logic that goes into your fabric. And that number of wires is pretty much predetermined by the process node that you have, because you can only pack wires into a certain density, and you use 2 layers of metal to go horizontally and 2 layers of metal to go vertically about, and that kind of gives you an upper bound of the number of wires. So any architectural change I have to make, I have to live with that wire density. I don't have the luxury of adding more wires. In an FPGA, each wire needs a programmable point to connect, and there are very few of these programmable points because they are very expensive. In an ASIC, you can drop a via, you only have the number of wires you want. There are infinite ways you can drop vias, so you have a very efficient connection structure. So as a result, they can live with a lot less wires than in an FPGA, so they can shrink the amount of logic into a tiny bit, and the 3–4 wires that go over it is good enough for them to connect the amount of logic. So if you analyze it and go through each of the columns, you can easily convince yourself that compared to an FPGA, an ASIC can easily be 5 times to 10 times smaller in the logic block. A second issue that happens is, in an FPGA, we give you one size lot, fits all. So if we give you a 4-input lot, whether you have an AND function or a 2-input function or a 4-input function, it occupies the entire lot. You have not much choice in doing anything else. In an ASIC, you only put the gates you want. So some are smaller, some are bigger. So as a result, even the logic efficiency is a lot better in the ASIC. And if you take these two factors together, that's how you get the 30 to 40x better logic efficiency in an ASIC. If you hypothetically, if you think about it and remove the configuration RAM from a 2-dimensional logic block, even though it's only 27%, and do the math, now assuming you can make use of the reduced number of wires because you have a smaller footprint, and that you can actually interconnect using that, and solve for the equation, you find it's about 3–3.5x improvement. And in our 3D structure, we did achieve in the ballpark of 3.5 to 4x improvement in logic density. And the nice thing is, these all adhere to FPGA tools. So any design, any third-party tool can design and map your design into our fabric. And in terms of fabrication, this is very quick to fabricate. It takes us about a day to synthesize, a couple of days to close timing. And then for an ASIC, it takes 4 weeks to get the top layer metal and to ship it out to a customer. So we can get FPGA samples, of course, you can buy it, ASIC samples within 4 weeks of having a design completed. So the last slide, what I want to show is, you have to have a monolithic integration, because the number of connections we need are in the order of about 100 million per centimeter squared at 40 nanometer. You cannot get that kind of density in any other technique. So just to summarize, we have, I believe, unified an FPGA and ASIC design methodology with a bitstream concept of IC design. We have built the first monolithic 3D FPGA. Once you have a netlist, the same netlist goes to FPGAs and ASICs. And this is the only way, I believe, that you can actually improve what's under the hood of an FPGA. And thank you for your attention, and I'm open for questions.
Questions?
Alex Lomachnikov, HiCam Systems. It's very interesting presentation, very interesting ideas. But I was not sure, when you were talking about doing the mux in the 3D, are you planning to use thin film transistors for that? Because that is speed critical.
Yes. That's the holy grail. And the answer is yes, that's true. We actually did some experiments. We took a NMOS layer of thin film transistors, and we did a laser crystallization study so that we recrystallize the amorphous silicon into a single crystal. And we were able to demonstrate a 10,000 improvement in the mobility. Now, people say 10,000 is a large number, but remember, this TFT started being really lousy mobility transistors. So you don't need the bulk mobility because the capacitance of a thin film transistor is much lower. So if you can get the performance, you can size the thin film transistor, you can overdrive thin film transistors. You don't have to operate it at 1 volt or 0.9 volts. And the sum of the two can allow us to do that. We are not there yet, but I personally believe it can be done. There's a lot of research on these laser crystallization techniques to improve mobility for thin film transistors. So that's the idea. Okay. Yes?
This is a quick one. So I know John Swan on chip. So I know you got to walk before you run and all this stuff. But did you spend any time thinking about how this might apply in the future to MRAM memories up in the routing layer? Just curious.
So the answer is no. I've been on a one-track mind. My mind has been only in trying to get this FPGA concept going. I think there's a lot of research that is being done in trying to build a second layer of transistors on top of first layer of transistors. Mobility and power dissipation being the front runners of how does this technology evolve. So my initial thinking is I'm not trying to be smarter than a lot of these university professors. They will outsmart me any second. But to make use of applications where power generation is not a concern, and so certain types of applications which lend very well into FPGA arena. Even muxers don't actually generate a lot of powers. Those are inverters and buffers that leak like crazy. So as long as we stick to these kinds of concepts, I think it's very easy for us to walk that path. Okay? Yes?
John Davis, Microsoft Research. Can you give us a sense of the operating frequency range of your devices?
So we find, without trying very hard, for a certain number of logic levels, we get about 20 to 40% performance improvement over a comparable two-dimensional FPGA node.
In that technology node or in
that technology node. So for 90 nanometer, if you take a 2D FPGA, ours is, so I had done back of the envelope calculation, and I expected to get about a 70% performance improvement, and I didn't get that. So I went back and asked the guy who designed it, saying, how come we're not getting there? And what happened was that every wire we have, it connects to all these potential programmable points because you didn't know which logic block is going to talk to that wire. So we have this prefabricated heavy loading technique. And since my logic has come together more, I have more of this hanging off of the wire. So that accounts for the fact that we went and we didn't gain the total L squared improvement we were expecting. So we came up with a new invention, which is once we know which logic block goes to the wire and how it enters a logic block, all the other points are absolutely unnecessary to be connected. So with a second metal change, if I wanted to, I can get rid of all those additional connections, plus all the pass gates are resistors. I can short the source and drain of that. So with a simple metal mask edit, I can get to a 2x performance improvement over any FPGA. Now 2x in this day and age, you will note is a significant improvement because going from 40 to 28, as some experts showed us today, you hardly get any performance improvement. So that's a big improvement. And of course, going into a third layer, we should be able to get easily another 40, 50% on top of that.
And how much memory are you putting on the device?
In terms of Block memory or configuration memory?
Block memory.
Okay, so block memory to me is trees. You can add however much trees you want into a forest as you want. So there's a general rule of thumb that the Alteras and the Xilinx define the world. Here's a ratio. You guys get used to using this ratio. So anybody who strays from that kinds of pays a penalty. So to me, it's not very interesting. We can put whatever memory anybody wants.
Thank you.
Okay.
James Tringali, Rambus. Looks like some nice work. Going into the third dimension gives you effective economy of scale, if you will. But there are some issues with going into 3D and increased costs in the processing steps and potential yield loss as you go higher.
Yes.
Can you comment on your experience with those things?
So every time I go in front of a VC, I have to answer these two questions. So I'm very familiar with that. So the nice thing about area and material cost is the defect density or the yield model is exponential area times defect density. So it's an exponential function of the area improvement. So if you can improve the area, the gain you have is exponential. The building materials are linear. If you add an extra process step, you can calculate how many steps you are, and you get a linear increase. So we typically add about 25% to a standard CMOS process to build that extra thin film transistor layer. Based on the yield calculation, because it's a static circuit and because we operate with very large margins, we find that the defect density improvement or reduction is negligible. The CMOS pretty much determines your yield, and these TFTs work like gangbusters because they are not dynamic circuits. They're very tolerant of a lot of parametric issues. They only fail if there's a gross oxide defect or a metal short, and those things are very rare these days. So as a result, right, the yield loss is almost negligible. The cost improvement is 25%, but that's only true for the FPGA version. Once we go to the ASIC version, it's a regular ASIC. It's a standard CMOS process. It's the same cost as any other ASIC process.
So I imagine in the Holy Grail scenario, that would be more of an issue because you're trying to put dynamic circuitry.
Right. That's right. But,
go ahead.
Yeah. So I will follow that concept, and hopefully there are smarter people than I in this audience. So one thought process is if you take an ASIC, and if you can have, for the same density, power, performance, a prototyping device, which is incredibly expensive, how much would you pay that will allow you to design that ASIC and prototype instantly? And my answer is I can bundle it with the tools. And since you're paying 2 million or 3 million for the tool, why not pay 4 million? And I'll throw you a few prototyping devices. So in that scenario, the cost of that structure is not important. It's how easy is it for you to get the ASIC out of it. The reason FPGA cost is important is you can't really get the ASIC at the end of the day. Right? So the closer you can come to getting to an ASIC density, the less important it becomes, in my opinion, what the cost of that device is, because anybody will only do it for prototyping and initial validation, and they have this easy migration without any effort. They'll go do the migration. Right?
Thank you.
All right.
Okay, let's thank the speaker.
Thank you very much.